Okay, so here, as we discussed previously, the net available power from a wind turbine is given by W dot equals to half Cp rho into A into V in whole cube, where Cp is the power coefficient. Basically the efficiency eta, we are calling it power coefficient because that is what is used in the literature, and is the fraction of wind power that is extracted by the turbine. Okay, and A is the swept area of the blades. If the blade diameter is d, this is equals to pi by 4 d square, and V in is the wind velocity upstream of the turbine. And we want to evaluate Cp max under ideal conditions. What is the maximum conversion that you can get in an idealized wind turbine condition? So let's look into that. So now we will draw a schematic. So this is your wind turbine blades. So this is basically your streamlines that are moving through the swept blade area from upstream side to the downstream side. Okay, so we will see why there is a change in the cross section. So under the condition of ideal inviscid flow, we can think of this section as the set of streamlines that are moving from far upstream of the blades through the moving blades to the downstream region. Okay, and exiting far downstream of the blade area. So this is kind of your set of streamlines or stream tubes. Okay, and this is far upstream, and this is far downstream. And how do we define the far upstream and the far downstream? Basically, the impact of the wind turbine is no longer felt by the time you reach the far downstream, and they are not felt in the far upstream as well. So you have a certain velocity V in, which is constant as the wind is entering this section. Then the velocity slowly is changing, okay, and eventually it again reaches a constant far downstream, and you get a uniform exit velocity V out. So the point from which the velocity of the wind starts changing to the point where it stops changing is the region which is affected by the presence of the rotating wind turbine blades. And this is the region of influence upstream and downstream of the wind turbine, and we are looking into that. Okay. So this area here is A in. The total cross-sectional area of all the streamlines that are being affected by the blades. Okay. This area far upstream of the region, and this area is A out, which is the total cross-sectional area of all the streamlines affected by the rotating blades far downstream of the flow. And here you have A, which is the swept blade area. Fine. Now, because these are streamlines, they are all flowing parallel to each other. Okay, so there is no cross flow across streamlines by definition. So m dot in at the far upstream, m dot in, the total mass flowing into your stream tubes must be also the mass coming out at the far downstream. So m dot in equals to m dot here equals to m dot out. Correct. So the total mass through this cross-sectional area, total mass through the swept blade area equal to total mass at the exit far downstream of the blade area. So by conservation of mass, all of this m dot in equals to m dot out must be constant, because no mass is being lost in the system. So accordingly then, and we can also assume that the density of air is not changing. So rho A in V in must be equals to rho A into V equals to rho A out V out. Since density is constant, what this means is A in V in equals to A into V equals to A out V out. Correct. So this is one relation based on mass conservation. Let's look at what we do further. So by Newton's second law, force generated is the change in flow momentum with time. So work done is force into displacement, right? And force is basically either mass into acceleration, or if you think of a flowing system, it's the mass flow rate into velocity. Okay. So the change in flow momentum with time. Okay. So the force is the mass flow rate m dot into the change in velocity v. Okay. So what we are saying is, here is your mass flow rate m dot. Okay, the total mass flow rate through the system, and the change in velocity that this mass is experiencing is the force generated due to the blades. Okay. So m dot into the change in velocity. So this force is equals to m dot into V in minus V out. All right. Then the net power generated in the turbine due to this force is W dot. Now this is force. Force into velocity is power. And what is the velocity of the wind at the turbine cross section? It's V. Okay. So the force generated into the velocity of air at the turbine cross section is the net power generated by the changing wind speeds on the turbine. Okay. So this is F into V. So m dot V in minus V out into V. So this is the power generated in the turbine due to this force. Now what is m dot? M dot is rho A V, V in minus V out into V. So the final expression for net power generated is rho A V square V in minus V out. Okay. Right? Now, for ideal inviscid flow, that is flow this is basically potential flow, there are no frictional losses. The power generated in the turbine equals the rate of energy loss in the wind between upstream and downstream. What do we mean by this? If you have an inviscid flow, that is, there is no frictional energy losses, then the total energy transferred to the turbines is equal to the total energy lost by the wind. And what is the energy lost by the wind? It is the change in the kinetic energy between the upstream and the downstream of the flowing wind. That change in the kinetic energy is the energy that is being transferred to the wind turbine and is coming out as the power generated under ideal frictionless conditions. So this W dot must be equal to half m dot V in square minus V out square, the change in kinetic energy. That is half rho AV V in square minus V out square. So now we will equate these two terms, this W dot with this W dot. Okay. Let's equate this, and if we equate this, so equating and simplifying, we can remove many of the rho, A, V, those kinds of terms. V in square minus V out square is V in minus V out into V in plus V out. Okay. And this V in minus V out can be cancelled out with this V in minus V out. So when we do all of those things, we get V equals to V in plus V out by 2. Okay. Remember what this V is. This V is the wind velocity at the turbine blade section. So this is V in, this is V out. Here is your V. Okay, so in this section you have V. Okay, so this V under ideal frictionless conditions is V in plus V out by 2. So this V equals to V in plus V out by 2. Okay. So now let's go to the final part. We define a velocity ratio X as V out by V in. Okay. The ratio of the output velocity, outlet velocity at far downstream by inlet velocity in the far upstream. Then we can write under ideal conditions V is equals to half V in into 1 plus X. Okay. Now if we put this expression V equals to half V in into 1 plus X, and remember what W dot is? W dot is rho A V square V in minus V out. Okay. So we can write rho A, instead of V square we will put this expression. So half V in 1 plus X whole square, and we take V in out here 1 minus X. Alright. So what we are basically trying to do is expressing everything in terms of the velocity far upstream of the wind turbine, which is actually what the wind velocity is, right? The wind velocity, the normal wind velocity, if there were no wind turbine, is your V in. So that is the wind speed distribution that we are talking about. So we know the wind speed distribution of the average wind through anemometer readings, etc. Okay. So V in is known. So we are trying to express everything in terms of V in now. Okay. So this becomes then equal to 1/4 rho A V in cube 1 plus X whole square into 1 minus X. Okay. So this becomes your W dot. Alright. But note, our original expression for W dot was half Cp rho A V in cube. So if you compare these two, you have rho A V in cube here. Instead of half Cp, we have 1/4 of this. Okay. So this means that your Cp is given by half 1 plus X whole square into 1 minus X. So this is your expression for power coefficient in terms of the velocity ratio V out by V in. So this is the generic case, correct? Now let us discuss when does Cp tends to Cp max. So what is the maximum possible value of this power coefficient Cp? So this, of course, it's a variable only with respect to X, which is V out by V in. So we can set dCp dx and set it to 0 to get the stationary value, which is the maximum. So if we do that, we differentiate this Cp with respect to X and set it to 0. So we basically get 1 minus 2x plus 3x square equal to 0, which implies 1 plus x into 1 minus 3x, basic algebraic factorialization, which implies either x equals to minus 1 or x equals to 1/3. Okay. Now there are two physical solutions. This is of course a So this is a cubic equation. A differentiation with respect to x gives you a quadratic equation. So you have two roots. Okay. Now x equals to -1. What does that mean? It means the V out will be equals to minus V in. All right. So let's go to the previous example figure. So this V out has to go this way. Now this is impossible for our wind turbine case. Remember, this is exactly what happened for your Pelton turbine water turbine case. You hit your V in was this direction and your V out went this way with respect to your Pelton turbine. Correct. So there the water moved this way and then came out this way with respect to your turbine blades. Alright. That can happen for that specific type of water turbine case. Alright. But here you have a wind turbine where the velocity is moving smoothly from downstream to upstream in the same direction. It's decelerating, yes, but it's not going the other way. It does not make any sense to say that the wind after hitting the blades moves back this way. It does not happen. Okay, this is a continuous flow system immersed in your atmosphere. So such systems cannot generate this V out opposite of V in. Okay. So for these kinds of systems, this is not possible. So only remaining physically plausible solution is when x equals to 1/3. So when you have V out by V in equals to 1/3. That is the other case where CP can be maximized. Okay, so two cases. So CP gets another stationary maximum value when V out by V in is equals to 1/3. That is the outgoing velocity is 1/3 of the incoming velocity and in the same direction. So if you put this expression here, x equals to 1/3 here, then CP max is equal to half of 1 plus 1/3 whole square and 1 minus 1/3 implies CP max equal to 0.593. Okay. So in this expression then, W dot equals to half CP rho A V in Q, we get W dot max equals to 0.593 into half rho A V in whole Q. Okay. So this is called the Betz limit. So the maximum possible conversion of the available wind power to the rotational power of the wind turbine blades is 59%. So around 59% of the total kinetic energy present in wind can be converted into mechanical energy of your wind turbine power. Okay, it's not 100%, it's 59%. That's the maximum limit for ideal frictionless flows. So there are other efficiencies associated with inefficiencies associated with frictional losses, motor losses, wind turbine blade friction losses, etc. So ignoring all of that, the maximum limit you can hit is the Betz limit, which is 59%. Okay. So that is kind of the maximum limit. And we can also say that modern wind turbines have CP of the order of 0.4 to 0.5, which is 70 to 80% of the Betz length. Okay, so that's the current state of the art technology can convert about 40 to 50% of the available kinetic energy of wind into mechanical energy of the wind turbine blades, okay, which is around 70 to 80% of the ideal base limit, which is not that, which is fairly okay. Okay, we cannot expect more than that actually. All right. So with that, I will finish today. We will discuss further on base limit a little bit more, and then further examples and ideas of these things will follow. So with that, I am stopping for today. We will discuss further in the next class. Thank you for listening and have a great day.